minutes. Yeah, basically there should be a seconds count. Do you start? Do you start again?
Yeah, I started. So the thread that is breaking, that's okay.
And it's counting.
Yeah.
Okay. So, welcome everybody. I hope you guys had a more or less relaxing spring break. Yeah, so if you haven't handed in your homework yet, the stacks are up here in front, or email them. So just make sure you email it out today. The new homework will be out sometime in the evening today. Exact timing is yet to be determined, but basically we just want to make sure that the homework is a reasonable amount of workload and not too much. Okay, now, so there have been various comments, feedbacks, and so on about both the midterm and also about the class. And if you look at the score distribution just in terms of raw points, so that doesn't mean final scores, but just raw points from the midterm, well, some people got an amazingly high number of points. So they got something around 85 out of 100 raw points. So this is not final points, but raw points, which is more than what I thought anybody would be able to achieve without really pushing themselves very hard within 70 minutes. So this is insanely good. On the other hand, there's also a non-negligible number of people who scored something like 20 to 25 points. So they scored something like a quarter of what the best students did. This is less than what I thought should be reasonably comfortably possible, given the homeworks and given the lectures. So for instance, if you take something like the VC dimension estimate, well, you know, if you have n linearly independent basis functions, well, you can basically already appeal directly to results from the lecture to say, okay, n linearly independent basis functions have VC dimension n, and that would have been the entire answer for that question. And you should have been able to extract that without an insane amount of pain from the lectures. Or the perceptron algorithm, which was there in great detail, and all you would have had to do is just step through it on paper. So those are the kinds of questions where I thought it should be relatively easy to get. I know there were some rumors that, well, certain types of questions would not be asked in the exam, but as you know, rumors are just that, and until they are confirmed, they are rumors, and you shouldn't actually prepare for an exam based on rumors. So, two take-home messages. Doing the homework will help you for an exam. Going through the slides will help you for an exam, so that's the one thing. The second thing is, rumors are rumors, and if you base your plans what to study on a rumor that somebody randomly spread in class or on any discussion group, then you're screwing yourself. Okay, so don't do it. Okay, question, yeah? Okay, so they will be available later this week. So we'll make sure that the results are okay in the end, but we also want to be fair to the guys who did insanely well. So, yeah. Basically, which brings me to an interesting point. So I know this is a star class, so that means that you're more or less required to take this or the AI class, right? And I know that most of you are not core machine learners. And then we also have that curriculum. And you've probably seen that Barnabash has slowed down a lot in the past few classes, and he's gotten really good feedback for that. So a lot of people are very grateful to him for this. Okay. There's a little problem with this. If we slow down as much as that, there's absolutely no way we'll get through the curriculum, right? Because the curriculum is just a lot more. And then if somebody asks you later on, you know, basically, you know, you took the 701 class, you're supposed to know all those things and you don't know them, well, that's not good either, right? So we're caught between a rock and a hard place. The rock is, we'll do less and go very slowly through it. And you'll remember that, but we will not be able to cover the entire curriculum. The hard place is, well, we'll try at least with some effort to cover a reasonable amount of the curriculum, but it's probably not going to be easy listening. Okay. I'm open to both suggestions. And unfortunately, one of those two things we'll have to give. And those of you who actually have all the background and would be happy with a faster class, I'm sorry, yeah, I cannot adjust to you guys because otherwise nobody will get anything out of it. I'm really sorry. Okay, so I need a vote. And I need everybody to vote here. And I want you to understand that whatever we decide now, don't go afterwards on the Google forum and complain that we didn't do the opposite, right? Because there seems to be a very different vocal population on the forums from whoever speaks up in the class. Okay, so whatever the vote is now, this is what we're going to do. Okay. So vote 1 is we go through things very slowly and we'll miss out on substantial parts of the curriculum. Vote 2 is we'll go through things at a, well, more accelerated pace. Well, not quite as fast as when I started, but more accelerated pace. And we'll try to make a best effort to cover most of the things in the curriculum. Okay, that's option B. So, who votes for option A? Okay. Okay. Who votes for option B? I think this is the minority. It's probably 2/3 majority who votes for option A. Okay. So, therefore, we shall go through things slowly, and we will not get to everything in the curriculum. If you need to cover things, need to understand things that are not in the curriculum, that are in the curriculum and that we will not be able to teach, there are two things. First of all, I'm happy to point you to any suitable book that covers that specific area. Okay. So ask me, for instance, in the office hours, and I'll point you to something. B, well, you take the 701 for the core ML students. C, you find, for instance, some lectures that I, let's say, for instance, taught in Berkeley last year, or you find some other classes that cover this. Okay, good. So with that out of the way, I need your help to make sure that I'm not going too fast. Whenever I go too fast, raise your hands, ask questions. I've said it several times, but basically if something is not clear to you, almost certainly it's not clear to somebody else in that room too. You can actually work out that probability. Okay, so given that it was quite a while ago, let's just recap exponential families, just because, yeah, it's been about 3 weeks, and I am fairly sure very few of you remember this thing. Okay, so this is really just the formal definition, and unfortunately those first 2 lines you need to remember. So basically P of x is given by E to some inner product between some statistic phi of x, and we'll go through a lot of different examples of what you can plug into phi of x, and some parameter theta. So this theta can be just a number, can be a real valued variable. This can be a dot product. So phi of x could be in 3-dimensional space, let's say. And then this g of theta does nothing else but just ensure that this function is properly normalized. So in other words, we can actually compute g of theta by the condition that the integral dx e to the phi of x dot theta minus g of theta equals 1. Okay. Now you can immediately see, yes, you can see, that's good, that this term here doesn't depend on x. So I can pull it outside the integral and have e to the minus g of theta. So I can bring this over to the right-hand side, and we get that the integral dx e to the phi of x dot theta equals e to the g of theta. And then all I do is I take the log here, I take the log here, and I get that g of theta is the log of that integral. Right. Now, the only thing that you would have seen differently in the slides is that we have a sum rather than an integral. And basically, I'm just being a little bit sloppy here in order to ensure that we can deal with both continuous and discrete random variables at the same time. Now, one thing that is important for continuous random variables is that you need a measure. And if not stated in any other ways, we'll just use the Lebesgue measure. So the standard thing that you would use for integrals. Who's heard of the Lebesgue measure before? Okay, that's probably about 1/5 of the class. So basically, what you need to do is, if I have an interval, okay, so I'm not going to do the mathematical definition here, but basically just to give you an idea of what's going on. If I have an interval of size 1, it goes from, let's say, 0 to 1, I need to determine what the weight of that interval is, right? And most of you would intuitively say, well, you know, that's 1, right? And if I have another interval of size going from maybe 0 to 3, you would say that that piece is probably, that weighs 3. So what a measure does, and I mean, so if you're a mathematician, you'll cringe now, but it'll basically take a set x, and it'll map it into some number mu of x, and that number is, well, greater or equal than 0. This is very close to a probability distribution, but it's not quite the same thing. So first of all, the integral over an entire domain, well, you know, it can be actually infinity. So if you integrate from minus infinity to plus infinity of the constant function, well, you get infinity, right? So that's one of the differences between a measure and if you actually have a probability distribution. So there, if I, you know, take the integral over the entire domain, well, it better integrate out to 1. If it doesn't, so I'm in trouble. Okay. So, and yeah, if you've taken any math class, try and see whether you can read up a bit on measure theory, but this is as much as you need to know. Now, why do we care here for the exponential families? Well, we are later going to encounter the Poisson distribution. And the Poisson distribution is a distribution on numbers from 0 up to 0, 1, 2, 3, up to infinity, right? So it's a distribution on A. And, well, there are various ways how I can count. One way how I can count is just, well, I count the number of numbers in the set, and that's the measure of that set. So let's say I have a set which contains 4, 5, and 9, then that measure would be 3. And that's, you know, the most default standard thing that you could do. However, for the Poisson distribution, we are going to use a slightly different measure. We are going to use the measure 1 over x factorial. Okay? So that means 1 counts 1, 2 counts 1/2, 3 counts 1/6, and so on. So based on that measure, our set 4, 5, and 9 would have the measure 1 over 4 factorial plus 1 over 5 factorial plus 1 over 9 factorial. Well, so that looks a little bit crazy. Turns out that this makes a lot of the math later on really nice. So just be aware of the fact that when you have a domain, you need to define a measure on that domain. And if you don't do that, well, in many cases you can get away with, whatever generic definition you would use. But yeah, other than that, yeah, just be aware of this. Okay, so mean and variance, we went through that before the spring break in a lot of detail. And if you'd recalled that derivation, that would have pretty much given you the solution to one of the problems in the assignment, in the midterm, right? Remember, there you had to compute the cumulative generating function and take derivatives, and the only difference was that you would have basically had to treat the original underlying distribution exactly as that measure that I just referred to. So in other words, those 3 lines from the top would have been the solution to one of the questions in the midterm. Okay. So given that that's actually all on video, I'm not going to go into a lot of detail here, but I'm happy to answer questions if you have anything about the derivation. Any questions here? Okay. So let's just go through the examples again. So the binomial distribution, well, phi of x, well, it's just x, and x is taken from a set of 0 and 1. Okay, so these are the 2 outcomes. So it's like heads or tails for a coin. A discrete distribution, phi of x in this case, I'm just making this to be the canonical unit vector. And let's just take a simple example. Let's say, for instance, I want to model the distribution of languages on internet web pages. And for whatever reason, my set only contains English, French, and Spanish. Okay. It's a very limited set, but I think it's not uncommon in North America. So now En, so this is my domain, would be the vector 1, 0, 0. EFR might be the vector 0, 1, 0. And ES, like Espanol, would be 0, 0, 1. And so now I can use this to model a probability distribution over those 3 languages, let's say, on web pages that I encounter. For a Gaussian, it's a little bit more complex, and we'll go through that in a bit more detail later on. It's basically phi of x is x and 1/2 xx transposed. And so what you already notice is that not all the coordinates in this phi of x need to be really of the same flavor, right? So the first d coordinates in this case would be, for a d-dimensional Gaussian, would be just, linear functions of x. And the next d² coordinates would be quadratic terms. On top of that, I didn't actually require that these vectors are all linearly independent. Okay. Can somebody tell me, if I have this mapping, x mapped into x transposed, and x is in Rd, what the dimensionality of the spaces that xx transposed really maps into? Okay. So d², yes, that's the number of coefficients that I have. What's the number of independent dimensions? Perfect. Exactly. So the idea is, well, let's take this matrix here. It's a symmetric matrix. And we have all the on-diagonal elements. And we have, let's say, for the loss of generality, the lower diagonal elements. And those are equal to the upper diagonal elements. So in order to really represent all of that, that's the only thing I need. And that, yeah, just works out to d times d plus 1 over 2. Okay. So, and you could actually express everything in just those coordinates, but that would just look the algebra make it look ugly. So I'm not doing that. Okay. So let's actually go through a very specific case, namely a binomial distribution. So remember there we had phi of x is x. And so, well, p of x, let's just work it out. For x equals 0, well, what do we have? We have e to the, well, phi of x is 0, 0 times theta, divided by, now I need to make sure that everything normalizes out, so I have e to the 0 times theta plus e to the 1 times theta, which is nothing else but 1 over 1 plus e to the theta.
Just one comment.
Yes.
There was an answer that said that the freedom is d, and that's right if you calculate the freedom of x transpose, but if you calculate the freedom of a symmetric matrix, that's d times d plus 1 over 2.
Yeah. Well, that's what we have there.
Yeah, but if we just ask the freedom of x transpose,
Yes.
then the freedom in x is just d, right? So
Yeah.
x transpose is just d.
Yeah. Okay. Thanks. So I guess I don't have to walk you through p of 1 in this case, right? Because that's just, you know, e to the 1 times theta divided by this. And then you get the second equality by just dividing by theta. This is the very simplest exponential family distribution you can come up with. Well, okay, there's a simpler one which is basically just a constant, which occurs on the empty set, right? Which has no parameters whatsoever, but that's such a pathological case we're not even going to bother about it. Okay. Are there any questions about this? Are there some events, or some probability distributions that you cannot model with this parameterization? Are there some p of x's that for which I cannot find a theta? Okay. Hint, what happens at the boundaries? So p of x, so p of 1 equals 1 or p of 1 equals 0 are probabilities that I cannot explicitly express in that parameterization. So those are terms that sit exactly on the boundary, right? And so this is one thing that you need to be careful of in an exponential families notation, that sometimes there are interesting things happening on the boundary for which the parameterization is insufficient, but only okay in the limit. This looks like a major problem, but it actually usually turns out to be a big advantage, because in many optimization problems you actually want to have some function that keeps things within the scope of, let's say, probability distributions. So later on for a Gaussian, we will have things like log determinant of a matrix. And that will ensure that, well, you can't have negative variance or variance 0, right? Because then the log determinant of that matrix would be infinity. And so this is one of the, this is one of the reasons why sometimes actually switching to an exponential families representation will make your optimization procedure easier to deal with. The last thing that we already covered 3 weeks ago also is that this function g is convex. Okay. So this log partition function here in this case is very simple. It's the log of 1 plus e to the theta. Well, we can just plot it, right? Here's theta, and here's g of theta. And so, well, what we'll have is at 0, it'll be the log of 2. And it'll asymptote into something linear, and it'll go upside. I mean, if you fire up MATLAB, you can get a more beautiful plot, but if you look at this, you can see that it's a convex function. You can also take derivatives and check it manually, but the good thing is that all such functions g have to be positive semi-definite. Okay. So that's kind of nice, but can we do something useful with it? Well, the first thing is that we can just, look at the expectation. And that, as we saw before in the general case, is the derivative of this function. So this is good, because now after we've done all the painful work to compute g, we can compute expectations and also variances very cheaply by just taking derivatives. So let's do that. So d theta of g of theta, well, just applying chain rule, is e to the theta divided by 1 over 1 plus e to the theta. And lo and behold, that's exactly p of 1. And that works out fine because, well, the expected value of x is just p of 0 times 0 plus p of 1 times 1, which is p of 1. Okay. Now, the variance is something where, you'd have to think a little bit more carefully. Let's just actually work it out explicitly before. And the good thing is that it basically protects you from having to think. So, the variance of x is the expected value of x squared minus the expected value of x squared. So this is nothing else but p of 0 times 0 squared plus p of 1 times 1 squared minus, and we already have that quantity here, right? We computed it before. So we have minus p of 1 squared. So this is nothing else than p of 1 minus p of 1 squared, which is just, I can bracket out, p of 1 times 1 minus p of 1, which of course is p of 0, because that's the only other thing that could happen to us. And, well, lo and behold, that's what you also get if you just work explicitly those derivatives here. So all I've done is just I've taken the derivative of the first term here. We say, lazy, you could just plug that into Maple or MATLAB or whatever, and you'll get that constant. Yes?
Why calculate fun in terms of derivatives?
Fun?
I don't quite understand why it's the derivative.
Why it's the second derivative? Yeah.
Or even for the expectation as well.
Okay, so that was this slide here. So that's what we did before the spring break. So it's actually discussed in about 10 minutes of video. Do you want me to go through it again now, or would you rather just watch it at home on YouTube? Who wants me to go through it again now? Okay. Okay. 2 votes. I guess that's not the majority. But basically, for the moment, you just have to believe me that this math here says that it is. So, I mean, all you do is you just brute force work through d theta of g of theta, you rearrange terms and you get exactly the expectation. You do the same thing for the second derivative, you rearrange terms and you get the variance. This is a really, really useful property because it means that you don't explicitly have to define things anymore. Once you read off those values, you're done. Mind you can get higher order cumulants in the same way. So this is really, really handy. Okay. Now, for the normal, any more questions about this? Yep.
Could you please repeat what you talked about the boundary cases?
Okay, so the boundary cases, by the way, thanks for asking questions. This is good. So the boundary cases in this case are, well, p of 1 equals 1 and p of 1 equals 0. Right, because for p of 1 equals 1 to be true, I would have to have, well, basically 1 over 1 plus e to the minus theta. I'm going to plug the solution in here. E to the minus theta equals 1. Well, right. So this is equivalent to e to the minus theta equals 0. And you can immediately see that, well, this would only hold if, theta were infinity. That's exactly the boundary. So in this case, we actually have a convex domain which is not compact. You may in other situations have a convex domain that actually is compact. But on that parameterization it isn't. And that's usually a good thing for optimization purposes. Because unconstrained convex optimization is so much easier to handle than constrained convex optimization. So this is exactly what you want. We started out with a problem where the probabilities were between 0 and 1, and we reparameterized it into something where now the parameters go from minus infinity to plus infinity. This is usually what you want. I know it doesn't feel like it right now, but as you actually perform optimization, you'll see that this is exactly what helps you. Okay. Any more questions? Yep.
I wonder why you call it binomial. Is there a probability?
Yeah, it's just basically two outcomes, yes. Yes. So, there's a normal distribution. I guess all of us have seen a Gaussian before. I'm not going to ask whether you've not seen a Gaussian, because if you have never seen a Gaussian before, you should not be here. Okay. But you might not have seen this one. This is the Poisson. And so this is how it's usually parameterized, right? So if you go to Wikipedia, you'll see that they'll write P of x parameterized by lambda is lambda to the x e to the minus lambda over x factorial. And you'd think, who dreams up something like this? So you can actually derive the Poisson by the following limit procedure, where I say, well, I have a certain event that occurs with a given expected value. Let's say, for instance, the amount of rain that I see in 1 minute on a square foot. But I don't know, well, basically how large my raindrops are and so on, and I want to model basically the amount of rain over an infinite, over many slices with very small drops. So what I do is I basically keep the expected value constant, but draw more and more and more observations, each of which can happen with a smaller probability. So let's say, for instance, in the expectation, I have 100 raindrops per minute, let's say on 100 seconds. Then I could do this, or I could say, well, I have an expectation 1 raindrop per second. But I could also then take a further limit and say, well, I might have in, 10 to the minus 3 raindrops, 1,000th of the probability 1,000th, a raindrop for a millisecond, and so on and so on. Now, assuming that all those raindrops fall independently of each other, I then get a distribution over raindrop counts, which now can vary quite a bit, because now each millisecond or each even tinier and tinier and tinier fraction will get its own chance. And the result of that limit procedure is exactly the Poisson distribution. So maybe, if you've never seen this before, maybe we can go over that limit procedure in the recitations. For the purpose of this class here, it's just a useful thing to know. Now, the Poisson distribution doesn't look anything like what I showed you before, but I'm now going to show you how you can rewrite this. So let's start with the solution, and that's just 1 over x factorial. Remember, that's the measure part. E to the x times theta minus e to the theta. So the statistic in x is very trivial. I mean, it's just x. And this e to the theta just so happens to be chosen in such a way that the sum over all x's for that really weird 1 over x factorial weighting sums up to 1. Now let's rewrite it into a way how we usually know it. And all I've done is I've just broken up the exponential. So that's what's happening over here on the right hand side. So I get e to the theta raised to the power x, because products and exponentials become exponentials of exponentials you know, as I disentangle things. So e to the minus e to the theta, well, it's just e to the minus e to the theta over x factorial. And then just matching up terms, you can see that lambda is e to the theta, and everything works out just fine. And yeah, there's a typo in LaTeX, because the x factorial should be in the denominator and e to the minus lambda should be in the numerator. Okay. So it's a typo. Any questions about how to match those two things up so far? So from that you can immediately see what the normalization is. It's just e to the theta. And from that you can immediately see that it's a convex function. The exponential is a convex function, right? Now, here the means and variances are super easy to compute, right? Because the derivative of the exponential is just the same function. As a matter of fact, that's the only function which has this property. Second derivative, same thing. And I challenge you to work out the variance just from the definition of the Poisson, you'll get mad. Right? This is not fun. Working it out this way is something that, you know, a high school kid can do. You know, you teach them that the derivative of the exponential is the exponential, and presto, they can do it. Another nice thing about this is that if we now actually know what the rate is, let's say, you know, it's 100 raindrops per minute on average, well, we set lambda equals 100. We take the log of that, and we already have theta. Right? So it's very easy. Okay, so again, that's this distribution. So nice thing to notice is, first of all, it's on discrete events. Secondly, it may or may not have a mode away from 0. So if rain is very, very, very unlikely, not like today, but maybe more like yesterday, then the most likely event would be that in a minute I don't see a single raindrop. Today we'd be probably more in the black curve, where the typical thing is that I will see some rain, but you could get super lucky very, very infrequently and have a second without a raindrop. Okay?
So is there any technique to define the theta? Because if you prove it from left side to right side, you prove it from the exponential family order to the
Well, I mean, it's an equivalence, right?
Yeah.
It's an equality. So the equality goes
Yeah.
in.
Yeah. I mean, so how can you? I mean, if you are given the the common version, how can you define the theta? Because you know the theta is.
You.
It is that.
Okay, so basically you squint at it really hard and you guess the solution. That's one way.
So it's kind of hard.
Yeah. Yeah. You could say so. The other thing is quite simply that you take an exponential you take this exponential expression and you check for which of those phi of x and which domains the integral works out. And there's probably about 150 years of mathematicians who've tried to do this. So chances that you will find a new such distribution are very slim. Just because, well, there are a lot of mathematicians, mainly French and German mathematicians 100 years ago, who without a computer solved a lot of those integrals. So good news is you can just look the stuff up. The bad news is, well, almost certainly somebody would have solved it unless you have a very specific setting in mind where people haven't done this yet. So for instance, for collaborative filtering, you can actually come up with interesting new exponential families. But in general, not so much. Okay, yep.
You explained the weight of each sample in previous lecture and showing the matter of the set. So how is the weight related to the probability?
Okay, so this is really just a way of defining, the distribution. And the distribution is defined by some measure on the underlying domain, and then a function that modifies this measure in such a way that I get something interesting. So, by the way, it's a good question. So if you look at the top left line, you see the measure appearing here. It's 1 over x factorial. And then the rest is this e to the x times theta times minus e to the theta. That's basically how I modify this measure in order to get an interesting distribution. To show you a little bit how this can get a little bit less trivial, well, let's take another distribution, so p of x parameterized by theta being, without that 1 over x factorial, e to the x times theta minus g of theta. This is the exponential distribution. And the slight difference that I'm making here is that, well, okay, let's actually keep x in A. Okay, so this distribution does decay less rapidly than the previous one. Before, we had this additional 1 over x factorial term, which just keeps things decaying very rapidly. This one here will, in general, for the same value of theta, decay less rapidly. Now, what we have to do is, we have to compute g of theta, which is the log of the sum for x equals 0 to infinity e to the theta to the x. Right? Now, does somebody know how to compute that sum? Okay. Have you done series expansions and sums of that at some point? Okay. So you've probably seen stuff like this, right? Sum over a to the n equals 0 to infinity. You've seen that kind of stuff, right? Same thing here. This is our a. So this is log of 1 over 1 minus e to the theta. Right? So now you see something very interesting happening here. This is actually, so can somebody tell me for which values of theta this is actually well defined? Negative values of theta, exactly. For theta equals 0, this thing blows up. Right? So this is only really well defined for negative values, whereas the Poisson is defined for any value. So, but this is, a perfectly reasonable log partition function. And you can check that minus log of 1 minus e to the theta is convex, and you can happily optimize over it. And this term here will ensure that you will never end up with a distribution with a sum that's divergent, simply because this term here will go to infinity if we pick theta equals 0. So that's an example where we used the same underlying domain, the same sufficient statistic, different measure, and we get a different distribution out of it. Okay? Does that clarify things a little bit? Okay. Any more questions? By the way, thanks for asking that question. This is good. So here's another couple of weird distributions. It's the beta. That will actually turn out to be the conjugate of the binomial. And we'll go through what it means to have a conjugate distribution later on. Here's the Dirichlet, which is, as it turns out, to be the conjugate of the multinomial. So here's what I want you to remember. So exponential family has this very simple parameterization. And you can use it to actually model a large number of different distributions. Yeah, question?
So if I have the ability to pick my own theta and my own phi, can I model any distribution this way? Because Because I can just take whatever
Yes.
theta I want and take the log of it and make that pi.
As a matter of fact, there are actually results that for not too pathological distributions, and that is a very mild requirement, you can basically find an exponential families representation. The only thing is that your phi may very well be infinite dimensional. If I have, general purpose distributions. So you could basically plug a reproducing kernel Hilbert space into this. So remember when we did kernels and Gaussian processes, we basically had those fairly rich function classes, and we wrote everything in inner products. And it's not a complete coincidence that I'm using the very same notation for this here as for what we used there, because you can take that entire machinery, plug it in there. If you'd asked this question about 10 years ago, you could have written a large number of papers from it. So it's a very good question. You can probably still write some papers about it, but now it's harder to get them. But you're spot on. So the other nice thing is if you have G, then getting the means and the covariance and also higher order cumulants is really easy. You just take derivatives. Now that sounds like it's, everything is great. Unfortunately, there are many cases where computing G is NP hard. Okay. Well, that puts a slight damper on this, right? So, who of you has done physics, as in thermodynamics, statistical mechanics? So you've probably seen this thing called Z, right? And then you have something like log Z. So this is something like the state sum. Log Z is G. So Z was, the sum over all possible configurations that you could have over the energies. And this phi of x dot theta is exactly the energy of your system. Okay. Those of you who've not had physics, forget about what I just said. But there is a reason why certain statistical inference techniques, like Markov chain Monte Carlo, for instance, are also really popular in physics. And mind you, I guess we all know that MCMC was essentially developed when they built the nuclear bomb, which was a very much of a physicsy kind of thing. So, and that would be a fun class to teach in its own right, to teach about, let's say, samples and connections to physics and so on. Okay, good. Now, let's do inference. So this should not be super surprising so far. The negative log likelihood. Well, if I have independent and identically distributed observations, it's just, the log of the product P of xi given theta, because each of those xi's is drawn separately. And since we have the exponential families representation from before, the exponential just goes away. This is one of the nice reasons why you use an exponential rather than another function. And then you just have g of theta minus phi of xi dot theta. Some people have actually tried doing similar things with log and exponential for more general function classes. And then you get all sorts of crazy entropies like Sully's entropy and so on. And again, this would be a cool class to teach, but fairly advanced level. Okay, now, if we want to maximize the likelihood, we have to take derivatives, right? And, well, that's easy in this case because we know what the derivative of g of theta is, right? We know that the derivative of g of theta is just the expected value. And so what we get is just, bracketing out m, and m and n are the same variable here. Yeah, sorry. Try to see double in case. So we basically get that the expected value of phi of x has to match the empirical average. Okay. Now, you've probably done this many, many times in the past. So for instance, when you observe some values and you want to fit a Gaussian, right? Let's say, well, we don't mess with the variance, but just the mean. What you would do is you would take the average of your empirical observations, and you would say, well, that's now the mean of my Gaussian. Or you might go and say, well, let's take the mean and variance as obtained from the data, and we plug that in for our Gaussian. And this is exactly what's happening more generally here. Or for the Poisson distribution, right? We would have exactly that condition. So now let's try this actually for our exponential distribution. Right? So we have that g of theta is minus log of 1 minus e to the theta. So d theta of g of theta is minus 1 over 1 minus e to the theta times minus e to the theta, so this goes away, we get e to the theta. So now we can divide again, and we get 1 over e to the minus theta minus 1. And this, we know, is the expected value of x for x drawn from that distribution p of x parameterized by theta. Now I go and observe some values. Let's say I have x1 is 3, x2 is 0, x3 is maybe 1, and let's say x4 is 5. Okay, so let's add terms up together. So I get 3 plus 0 plus 1 plus 5, well, equals 9. So I get that the empirical average is 9 divided by 4. And this has to be equal to 1 over e to the minus theta minus 1. So this is equivalent to e to the minus theta equals 1 plus 4 over 9. Right? And then you just take the negative log and you have it. Right? So in other words, theta is minus log of the log of 9 over 13. Okay. And that's how you would estimate parameters for the exponential distribution. If you had a Poisson, well, your life would be a little bit easier because you'd basically plug in 9 over 4 equals e to the theta, and you get the different quantity out of it. But that's basically all you do. So whenever you have a simple distribution and it fits in the exponential family, life is easy. And this is something that people knew about 50, 60 years ago. We are then going to move to stuff where it's not quite so trivial. So another example, binomial. So we have the log partition function and all that. Go through it, multinomial, same thing. So what you see here for the multinomial is we basically get number of counts for that particular event divided by total number of counts. And then for the Poisson, well, we have this thing here, same thing as before. Okay, so this is all really straightforward. Yep.
What is softmax?
Okay, softmax. Okay. Softmax is, I don't know whether it's like an official term, but it's used quite often. Is, okay, so first of all, the max of a set of a vector, max of x, is just, it's just max over I, xi. Now, this is basically max x. The log sum over I e to the xi is defined as the softmax. And you can easily check that the softmax is always greater or equal than the max. You can see that simply, you pick the largest term in x, and you know that exponentiating it and taking the log thereof doesn't do anything to it, right? Now, since after exponentiating you're adding something non-negative to it, it can only get larger. That's the proof. The other nice thing is that the softmax is differentiable. Actually, it's infinitely differentiable, whereas the max is clearly not. The max has this crossover region between two solutions. So this is why the softmax is often easier to deal with in terms of optimization than the max. Okay. Now, there's something you can do if you have a max but you want to make it computationally more tractable. Well, we can plug a lambda here and we divide by lambda here. So then for lambda going to infinity, this is going to converge to the max. You can check that. Because basically for very, very large lambda, of course the largest element is going to be way larger than all the others. And so therefore this will then win out. The only case when this isn't quite true is if I have, several elements in the vector that have the same value, then of course no matter how large I make lambda, well, okay, the difference is going to be log number of elements that have the same value. There's nothing I can do about that part. Well, actually it is, because it will still get divided out, but okay. Any questions about this so far? Because now we are going to move to something that's conceptually a little bit tricky if you've never seen it before, but it's very important that you get it. It's called conjugate priors. So pay good attention for the last 17 minutes of this class, because this is really, really important. Okay. So when we do inference, obviously quite often we don't have enough data, we have a very high dimensional setting or whatever, so it's a good thing if we actually have a prior on our parameters. I mean, you could call it a prior, you could call it smoothing or whatever. And, a good rule of thumb is you want to have at least 10 times as much data as you have parameters. If you don't have that, then you should definitely look into smoothing. Even if you have 10 times as much, it might not be quite so evenly distributed. So overall, this is a good thing. Now, another thing is, well, because it's a prior, quite often we have some idea of what kind of data we're likely to see. For instance, if you measure the voltage on a socket in the wall, well, you have a pretty good idea of what you're going to see. I mean, you're not going to see 10 kilovolts, right? You're going to see something, let's say, between 100 and 130 volts. Well, we're not quite sure, depending on how good the electricity is. Or you might see 0 volts because, well, simply you had, a cable failure. But those are about the numbers that you're likely to see. So you can encode that by just saying, well, let me dream up some values that are supposed to show up, right? And then what I can do is I could use them as a prior. In a way, that's the most natural thing to do. So I take my real data and I add to this real data some fantasy data. And that is, at its very heart, what a conjugate prior does. It adds fake observations to real observations. The nice thing is, though, that it does it in a way that doesn't necessarily require, let's say I have 10 real observations and I have 5,000 fake observations to make computation go as slowly as 5,000 fake observations. So in many cases it adds this fake data without really slowing down the inference algorithms. One nice thing about this is, of course, that then the posterior and the prior have the same functional form. Because the prior is essentially just a renormalized version of, what if I had seen some fake data, And the posterior is, well, what if I had seen some fake data and some real data? Okay, let me write this out in a little bit more algebra. So what I want is that P of theta looks like P of x fake given theta. So first question, why can I not write an equality here? What is different? Basically, what do I need to do in order to make P of x fake given theta into a prior P of theta? Any ideas? So, pardon? Sorry, can you? You might use randomization. Well, yes, you could, but that there's something fundamentally wrong with saying P of theta equals P of x fake given theta. Right? So P of theta is a distribution over theta. What is missing? What does a distribution have to do absolutely for it to be a distribution? It has to sum up to 1. Exactly. So what I can do is, therefore, I can write P of theta equals P of x fake given theta divided by the integral of P of x fake given theta d theta. Then it's okay. But I'm not allowed to just say is equal. Okay. So now let's tease apart what P of x fake given theta actually looks like. Well, let's just write it out. So that would be in the exponential family notation. And this is when conjugates work really well. Is e to the, well, now I have sum over x in x fake, phi of x dot theta, minus size of x fake times g of theta. Right? Now I'm just going to make two redefinitions that will make my life a lot easier. I'm going to define m0 to be the size of x fake. So that's like, how much, unreal data I'm injecting into this. And I'm going to define mu naught to be the mean of this quantity here. So I'm going to define it to be 1 over m0 times sum of x in x fake of phi of x. In doing so, I can write P of x fake. So actually I don't need this anymore. I can just work in m naught and mu naught directly. Parameterized by theta is e to the, well, m0 mu0 dot theta minus m0 g of theta. Okay. Let's look at a specific example. Let's say x is in the set 0 and 1. Phi of x equals x. Okay. Can somebody suggest reasonable values of m0 and mu0 to me? Okay. What would you pick for m0? You could pick 1. Yeah? So 1 basically means I'm going to give my observations the benefit of doubt of having one extra observation. Well, you might do that if you really don't trust the guy you're dealing with, right? Let's say you play tossing coins with me, and you know I'm really trustworthy. So what M0 would you give me? You'd probably give me 10, yeah. Thank you. Okay. Banabash might get 100. Okay. Now, let's say, what would we pick for mu0? Yeah. 1/2 is a pretty good idea. It's a good idea because that just means, well, I really don't know if I'm tossing coins, you know, whether heads or tails are going to come out. Okay. Now, let's say you go somewhere, you know, maybe a slightly dodgy place, and, you know, you toss coins, heads or tails. You don't trust this guy, and he says, well, you know, I want heads. Right? And he pulls out a special coin from his pocket, right? Okay. What would be reasonable values of M0 and mu0 there? I mean, you don't trust this guy. He looks really dodgy. And he says, well, he's betting on heads. What would be M0? What would be a good number? 1. Yeah. I would do that too. You can even give him less than 1, right? You could give him 0.7. So this is one of the important things. This doesn't have to be integral at all. Okay. What would you pick for mu0? So let's say heads is 1. So basically 5 heads equals 1. Okay, so what would you pick for mu0? 1? Ah, you're really skeptical. I would have given him at least a bit of the benefit of doubt, so maybe mu0 equals 0.9, right? Right. I know he's probably going to cheat me, but at least, you know, give him a chance, right? Okay, so what I guess you can already see from this is that by picking M0 and mu0, you can encode in reasonable extents, you know, what you expect your data to look like. This is what's called a conjugate prime. Now, what I haven't done yet is shown you how to turn this into something nice. So, here's the cool thing. So, we need to ensure that this integral works out to 1. And let me just write it in a slightly different way. So P of theta given M0 and mu0 is proportional to e to the, and now I'm going to do something strange. I'm going to write it as an inner product between theta minus g of theta on one hand and the vector of M0 mu0 and M0 on the other hand. So this is exactly the same as what we had here. I've just, you know, taken my theta vector and I've added one dimension to it. So my sufficient statistic of theta now is theta and minus g of theta, which I can do. And then, of course, what I need is I need a normalization. But we already know what that is because we've been doing exponential families all day today. So, and just to avoid clash of notation, I'm going to call it h, and it's a function of m naught mu naught and m naught. And it's the log of the integral of e to the phi of theta and the vector m naught mu naught and m naught d theta. And if I have that, I immediately now have a conjugate distribution. And this is really nice because now I can easily go and incorporate data. And we'll see in a moment that all that happens is that you just add fake and real data together. And where before that you had m naught mu naught, you're now going to get this plus the real data. Okay, so you already see that a little bit here. The posterior just looks like the prior. Okay, and let's go to the next slide and you see what's happening. So this is really just plugging in terms. Any questions here at this point so far? See, we had the likelihood term before. We had this before for the likelihood of x. We had this normalization. And what we just discussed were these terms, right? And now just multiplying them out gives us this. And so you can immediately see that this quantity here is exactly the updated mean times the new sample size. That's our new sample size. And this is very nice because I can just go and plug it in here. So, here are the updated equations. M0 goes into M0 plus m. And furthermore, M0 mu 0 goes into M0 mu 0 plus sum over I equals 1 m phi xi. Actually, I should have written it the other way around. Otherwise, if you implement it this way, you get the bug in your code, right? You see why? Because otherwise the M0 increments and then everything is wrong. But yeah, fine. And furthermore, we get that P of theta, given all the data, M0 and mu 0, is now given by exponential of, well, m naught mu naught plus sum over I phi of xi dot theta minus m0 plus m g of theta. That's what we already had here on the slide. And then we have a normalization minus h of, well, this term here, and then m0 plus m. That's it. So this is really awesome because what it means is that we can perform Bayesian inference and get the posterior distribution over the parameters in closed form. One of the reasons why this is so awesome is that people have done the work for us. So, as a matter of fact, for any self-respecting exponential family distribution, somebody has gone and worked out the conjugate distribution and everything's fine. And of course, you can also use all those tricks about the derivatives. And while this might look really abstruse here, why would I want to compute the expected value of the log partition function? This actually makes some of the distributed inference algorithms for scalable latent variable models go really fast. So this stuff is actually useful. As in useful to the point where it makes very scalable algorithms work. So there's a nice paper by Matt Hoffman and David Mimno and David Bly last year, ICML, where they do exactly that thing and it's very effective. Okay. So we're going to go through this the next class. Let me just quickly show you a table. And this is the table that you should remember at some point. So basically people have worked out this thing, and there are more distributions here. And just remember that whenever you need to do inference in this context, you can just look it up from a table. Okay. Any questions? Okay. So I said homework will be available sometime by tonight.